Hi, my name is Kurt Lundeen, and the topic of my research is adaptive perception, planning, and execution for robotized construction joint filling. A construction robot's need for mobility and loose construction tolerances produce large spatial uncertainties between a construction robot and its workpieces. The goal of this research is to provide construction robots with the ability to overcome such spatial uncertainties so they can perform detailed construction work. We use joint filling as our example construction activity to help evaluate and demonstrate our methods. The objectives of this research are to develop methods for the sensing and modeling of construction objects, to develop methods for adapting the robot's work plan to the geometry it encounters, to develop methods and hardware for the execution of work, and to demonstrate and evaluate such adaptive capabilities. To do all this, we developed a construction component registration technique that we refer to as generalized resolution correlative scan matching, which is a search method that uses multiple resolution levels to register models to sensor data. We also developed a framework for adapting a robot's work plan to its newly formed workpiece models, which involves the use of a Hampel identifier filter to remove outliers, a zero-phase moving average filter for smoothing, piecewise cubic interpolation to create a uniformly spaced smooth spline path, spline gradient analysis for tool orientation, and determination of tool speed from the gap's cross-sectional area and caulk flow rate. We also developed a pneumatic caulk dispensing tool for the robot. We then combined everything and conducted an experiment using an industrial robot arm. In our experiment, the robot expected to find a straight, uniform joint at a specific location, but instead we placed an undulating joint in a slightly different location to see if the robot could adapt. The robot scanned the joint, registered workpiece models to the sensor data, adapted its plan to the new models, and executed its plan to fill the joint. Shown in Figure 4 is a combination of the sensor data, the robot's modeling results, and the robot's plan for filling the joint. Shown in Figure 5 is a picture of the joint after the robot physically executed its plan. Shown in Figure 6 is a comparison of the joint's modeled profile versus its actual profile. And shown in Figure 7 is the modeling error. As you can see in Table 1, the robot identified the gap center with a mean positioning error of 0.18 millimeters and orientation error of 1.46 degrees, which is sufficiently accurate for a wide range of construction activities. To summarize, the adaptive perception, planning, and execution methods developed here appear promising for the robotic execution of a wide range of construction activities.